moves in a very fine path by applying positive potential and strike. I am calculating the wavelength of the diffracted. So you need electrons for the experiment. We are proving the wavelength. It is 1.66 angstrom. So there is a very close agreement. Hello students, this is SD Sir from the Temple of Excellence, Vidhyaashram Pre-University, Mysuru. Today we'll be taking up the last session on the chapter Dual Nature of Matter and Radiations. Enhancing back, our very aim to understand this chapter was to prove that moving material particles like electrons have wave nature associated with them. And we called this wave nature as matter waves. So, in my today's class, we will learn a very important experiment, a very classical experiment called Davisson and Germer's experiment, which establishes the wave nature of electrons. Experiment performed by two scientists, Davisson and Germer, which proves the wave nature of electrons. So this is the experimental setup, the experimental arrangement that was made by Davisson and Germer. If you observe F, it is a hot filament. F is a hot filament that is connected to a high tension battery. So F, hot filament connected to a high tension battery. When the battery is switched on, current flows through this filament. The filament gets heated up and electrons are liberated. So you need electrons for the experiment. We are proving the wave nature of the electrons. So from where will I get electrons? It is typically thermionic emission. Right? In the beginning of this chapter, you studied the different types of emission. Thermionic emission, emission of electrons from a heated surface. Here, the filament F liberates electrons when it gets heated up. Now, the electron beam moves in a fine collimated path It moves in a fine collimated path. Collimated andre single direction anta artha. Here I am applying positive potential and then make the electrons to move in a straight path. Adana technical agi collimated path ant karitivi. And this electron beam strikes a nickel crystal. So the filament F gets heated up. Thermionic emission is taking place. Electrons are liberated from this heated filament, collimated into a very fine path, moves in a very fine path by applying positive potential and strikes the nickel crystal. This electron beam is now diffracted. Please do know the word diffracted from the atoms of the nickel crystal and falls on the measuring scale. Diffraction of electrons is happening from the atoms of the crystal and it falls on the measuring scale connected to a galvanometer. Immediately, the galvanometer shows deflections, concluding that there is current in the experimental setup because electrons are moving. Understand? The atoms of the crystal diffract the electron beam, which are incident on the measuring scale. Electric current is constituted and confirmed by the deflections of the galvanometer. My dear students, the moment I say diffracted, diffraction of electrons, you know that it is a phenomenon that can be explained only attributing wave nature. So experimentally, here the wave nature of electrons is established. But I have to give a mathematical confirmation for that. Now, since I say there is diffraction of electrons, I consider an equation 2d sin theta equals n lambda, and this is from Bragg's law. I am calculating the wavelength of the diffracted electrons by using Bragg's law. And what does Bragg's law say? 2d sin theta equals n lambda. D is called spacing element. Theta, glancing angle. Lambda, wavelength. And what is this expression called? Bragg's law. From which what is calculated? Wavelength of the diffracted electrons, which turns out to be 1.65 angstroms. Now if I consider electron to be a particle in motion, de Broglie wavelength, lambda is h divided by root of 2mvq. Why de Broglie wavelength is coming into picture here? The electrons are in motion. They are treated as moving material particles. Therefore, their de Broglie wavelength lambda is h divided by root of 2mvq. And here, the value of lambda is 1.66 angstrom. Beautiful, alva. If you consider electron as a wave, using Bragg's law, the wavelength is 1.65 angstrom. If it is considered as a particle in motion, from de Broglie wavelength, it is 1.66 angstrom. So, there is a very close agreement in the wavelength of an electron, either when you consider it to be a particle or as a wave. So, the inference of Davisson-Germer's experiment, the outcome of Davisson-Germer's experiment is that it established the wave nature of electrons. So very clearly, the wave nature of electrons is established. 1 mark keltare. Usually they ask this question, what is the outcome, inference or result of Davisson-Germer's experiment? It establishes the wave nature of electrons. Now, we will now understand de Broglie's explanation to Bohr's quantization rule. Bohr's quantization of angular momentum as explained by Louis de Broglie. Now, we understand angular momentum of any electron in a stationary orbit is quantized. ಏನು ಬರೆದ್ವಿ ಮಕ್ಕಳೇ? ಬೋರ್ಸ್ ಪ್ರಿನ್ಸಿಪಲ್ ಏನು ಹೇಳುತ್ತೆ? mvr equals nh by 2pi. Very clearly you have understood this when we did our atoms. mvr is nh by 2pi. Quantization of angular momentum in a stationary orbit, where n was the orbit number 0, 1, 2, 3, etc. Now, if I consider electron is a particle, considering electron is a particle, then the total distance traveled by it in the circular orbit is 2 pi r, circumference of that orbit. Alva, see, I am treating electron to be a particle which is moving in a circular orbit. So what is the distance traveled by it in that orbit? It is nothing but the circumference of that orbit. Now, if I consider electron is a wave Then what is the total distance traveled by it? Distance traveled by a wave. It is nothing but wavelength, that is n lambda. So particle distance 2 pi r. Wave distance n lambda. But what is lambda? H by mv, de Broglie wavelength of an electron particle in motion. Substituting for lambda, 2 pi r equals n. Lambda is h divided by mv, or rearranging, mvr is nh by 2 pi. So again, very clearly from this, Bohr's principle is established. So Louis de Broglie also argues and confirms the quantization principle. Now, graphical representation of the variation of intensity with current. I told intensity is nothing but number of photons falling on a metal surface per second. ಒಂದು ಫೋಟಾನ್ ಇನ್ಸಿಡೆಂಟ್ ಆದ್ರೆ ಒಂದು ಎಲೆಕ್ಟ್ರಾನ್ ಲಿಬರೇಟ್ ಆಗುತ್ತೆ. 2 photons incident, 2 electrons are liberated, and proportionately photocurrent is constituted. So you can see, as the intensity increases linearly, photocurrent also increases. With increase in intensity, there is increase of photocurrent. And I want you all to do a small assignment. I want you all to study the dependence of photocurrent on potential. With this, students, I complete this chapter. Have a preview of this chapter. A very simple one. Repeated concepts which are very easy for the exam. In the next session, I start up with nuclei. Until then, have a nice time. Thank you.